guys, it's Ada. In this video, we're going to enter the topic of kinematics. And we're first going to start with the topics of displacement, speed, velocity, and acceleration. But to first understand what displacement is, let's understand what is position, or specifically the position vector. So in our coordinate space, the position vector basically defines the distance between the origin of the coordinate space and our selected point. In this case, A, and let's say it's 3 in the x-axis and 5 in the y-axis. This is an example of a position vector. Let's say that we had a second vector. Let's say that this is vector B, and let's say that this is 4 to, I don't know, -6. I mean, it's obviously not to scale, but that doesn't matter for now. So the displacement is basically the difference between these two distinct position vectors. The quantity of displacement gives us how much we traveled from the origin. That's basically it. So let's say that this is our position for A, and this is our position for B. Our displacement in this case would be xb minus xa. The difference of displacement and distance is pretty obvious, and there's actually a funny way to describe this. It's kind of like a joke. A lot of people say that if you were, let's say you were born in the hospital in your hometown and you travel all around the world, but heart attack, and you end up back at the same hospital. Your displacement is 0 because you started your life at the same point and you ended it at the same point. But the distance you traveled through your whole entire life would probably be enormous, depending on what kind of lifestyle you have. So, that's displacement, that's position. What is speed? What is velocity? And what is the difference between speed and velocity? Well, let's first understand what speed is. Speed is basically the total distance that we've traveled divided by the total time. Let's say that you have traveled 40 kilometers in 2 hours. You have a speed of 40 kilometers per hour. That's pretty basic. But velocity takes a measure of your displacement. So your velocity is the change of position, or your displacement in this case, and the change of time. If you don't know what this symbol is a Greek letter called the delta. And it basically defines some sort of change happening in a value. You can also show it like this, with indexes. Oh, I'm sorry. I'm writing this in Turkish. It's supposed to be xf minus xi, and tf. minus TI. The I usually stands for initial and F stands for final. So in this case, the total distance that you traveled would not matter. Let's say that you're trying to go to point B from point A. You can go like this, go like this, this. So your speed can change depending on which route you take. But your velocity would always take this route. Let's show that with a different color to make it distinct. Yeah. So that's the difference between speed and velocity. And you can also, in questions, they might ask you the average speed. And it wouldn't make a difference. The average speed is just the total distance divided by the total time. But why average? Well, we say average speed because there also could be an instantaneous speed or an instantaneous velocity. How? This is how. So, in a philosophical sense, to have speed, you need to have two different frames. Like, take this for example. Let's say this is a picture of a car. Now, I want to ask you, is there any way for you to tell me how fast this car is going? Not precisely, because to have speed, you need to have two different frames. If this is the first frame, A, and this is the second frame, B, to calculate the speed, you need to first calculate the distance or displacement if you're calculating velocity, and you need to measure the change in time. That's why we're saying average speed, because when you're calculating this, you're basically, what you could do if hypothetically you knew the speed in this frame and the speed in this frame, you could just take their average and calculate it this way. This is just the arithmetic mean of those speeds. But what if you would lower these distances? What if you lowered this displacement, and what if you lowered this difference in time? What would happen? And how much you could lower it? Well, for practical reasons, in the TIL-I exam, you won't encounter the topic of calculus. You won't encounter derivatives or integrals, and if you don't know what they are, that's completely fine. I mean, unless if they change the curriculum in the next years or so, but I don't think they would. So, you don't have to know those mathematical topics. But just to make this topic clear, I'm going to give you a little intuitive sense of what a derivative and what an integral is. So, let's plot, to make an example, let's plot a position time graph. Let's take just a one-dimensional case where this is giving you the position in the x and this is giving you the time. Let's plot a basic graph like this. Doesn't matter how it looks. So this is our position time graph. And so from what I told you before, to have speed, to calculate it, you need to have two distinct points, because it doesn't make sense to calculate it in a singular point, because there's no time. Well, what would you do to calculate the speed? You would take the difference in the position, take the difference in time, and divide those two. But isn't that kind of familiar in some sense? I mean, this calculation basically just gives us the slope between these 2 points. Of course, because these 2 points are too distinct from each other, it doesn't really make sense to visualize this as a slope. But what if I lower these values? Let's say that this is point E. Let's make it closer. Let's say that this is point C. And let's take the slope between these 2 points. It's still the same calculation, nothing is different, just the displacement got a little bit bigger and change in time got small. Let's make it even closer. Let's say that this is the point D. We can calculate this. Let's say this is point E. We can also calculate this. And so far, how close can we go? I mean, hypothetically, could we actually measure it in the same singular point? This is point E, but what if I get point B near enough so that it's basically at the same position of point B? Then what we're doing is we're calculating the slope of a singular point. That doesn't really make sense. But mathematicians figured out a way to make it have more sense, I guess. So what we're doing to find this is basically we're taking the derivative. What is taking the derivative? Well, let's say since our total distance was measured in time, the change in time, we need to calculate what would happen to our speed if our change in time got infinitely close to 0. So what does that mean? That means that our 2 distinct points got infinitely close to each other. They're not exactly in the same position, but they're infinitely close to each other. That sounds cheap to some people. That may not make a lot of sense. But in this video, I can't really make it make a lot of sense. I just want you to understand that the limit of our change in time basically describes how small we could make that change in time. The answer is infinitely small. So that in some cases basically means 0 in practical reasons, only in practical reasons, because theoretically, no, that's not correct. Limit to 0 does not equal the distance to be 0. But that's the topic for another video. So let's calculate this. So we want to calculate the difference in distance per the difference in time, while the difference in time got infinitesimally small. You can also see in here that why it wouldn't really make sense for time to be 0, because in that case this division would be undefined. It wouldn't exist. But derivatives help us defeat that premise. This is one way to show a derivative, and this is another way to show a derivative. dx over dt. This basically means to take the derivative of x per amounts of time. One important keynote here is that canceling out these d's in this notation wouldn't make any sense, because these don't just represent any other old variable. They're just a part of a notation, or a typical notation of derivative. So don't try to do this. Some people might get triggered. So now that I hope that you have at least a small understanding of what a derivative is, or at least what it helps us do, I guess you can understand what instantaneous speed is. Instantaneous speed is the calculation of speed for a singular time frame. Philosophically, that doesn't make a lot of sense for some people, but we're just here to do calculations. So you can just calculate the instantaneous as the derivative of the position, the derivative of displacement over the derivative of time. Also, another thing that needs to be represented that I forgot to tell just before, that velocity, since it is a measure of displacement over time, is itself also a vector. Speed is not. Speed is a scalar, but velocity is a vector. And we can do vector addition, subtraction, multiplication on these just as any other old vector. So, now hopefully if we understood what displacement, speed, velocity, and derivatives are, let's tackle another bit of calculus and another bit of kinematics, which is acceleration. Acceleration is defined as change in velocity divided by change in time. So just the speed measures the change in displacement. Velocity measures the change in displacement. Acceleration measures the change in velocity. And as you can guess, we can also showcase acceleration as the derivative of velocity for time. Or we can also show that this is also another notation, for which I need to remind you that you wouldn't see this notation in the TIL exam. I'm just teaching you this to not make you confused about the topic. Another notation is d squared x divided by dt. So this basically means the second derivative of position for time, which makes sense because in the first case we were measuring our change in position, which visually could be represented by the slope of this position graph at any time t0. And if we measure all of these slopes for all time frames, we can have ourselves a speed to time graph. So let's say that since this slope is kind of like 0, let's say that we are starting like this, and our velocity is increasing, let's say in a manner of linearity, kind of like a linearity. And then For some time instance, it again goes to 0, and then the slope gets negative. So it kind of starts to look like this. Since this is a vector notation, the negative and the positive only means direction in the sense of a one-dimensional action. If you have a singular line, you can represent these with a plus and a minus representing the right and left, or up and down, and these can change. It's just a preference to say that the left direction is described as a negative in front of the velocity. So we can measure the slopes of this graph and create this graph, and we can again do the same thing for this and create a graph of acceleration to time. And for this case, let's say the slope is same everywhere here, and this slope is positive, so let's say it's something like this. And this slope is negative, so let's say it's something like this. And you can get this from this directly if you measure the second derivative of it. That's the entire premise. But how do you get back? Let's say that you have an acceleration graph, like the previous one. Can you measure the, let's say, graph of the velocity to time from the graph of acceleration to time? It is quite possible, and the method we use is called integrals. Now again, this is a topic of mathematics, it's calculus, and I'm not going to get very deep into it. But basically, while taking a derivative of some value, we were measuring the slope in a particular point. To take the integral of something, we need to measure the area under our graph. Now that might not make any sense at this point because you don't know integrals, but basically integrals in a visual sense only is a way for us to get the area of under any curve. And for some diabolical mathematical reason, the calculation of area to a certain point gives us the graph of velocity to the same point. We could say, of course, to take this and turn it into this, we need to know the initial conditions of velocity. But let's say our initial velocity is 0, then if this is a constant acceleration, our graph would be like this. Negative acceleration, it would go something like this. And if you took the area under this curve, you could get the position to time graph. I'm not even going to show you the notation of this, or you know what, let me just show you. So the integral notation is something like this. We can showcase velocity as the integral of acceleration in respect to time. That's it. And This is the starting time. This is the ending time. Now, we're done with defining the terms. So, but before we get onto the calculations, there's also other things we need to understand. We need to understand a set of equations. These are called kinematic equations for constant acceleration. In a lot of real world cases, we don't really deal with constant acceleration because most likely, like any value, acceleration is changing. But in a lot of problems, we will encounter constant acceleration. For example, free fall problems where the gravitational constant of Earth is always considered the same anywhere. So it is a constant acceleration problem. And to solve these problems, we need to have an understanding of these equations. First equation is this, which is probably the most intuitive one. It's that the final velocity of our system is equal to the initial velocity plus the acceleration times the change in time, which is logical. I mean, you can derive this equation from this. If you say that final velocity minus the initial velocity equals to the acceleration times the change in time, this is just the change in velocity. And this is acceleration times the change in velocity. And acceleration is equal to change in velocity over change in time. And when you think about it logically, it's also intuitive because to find the final velocity, you need to first have an initial velocity and you need to add the change. And you can figure the change just by multiplying the acceleration times the change in time, because this would just give you the change in velocity. Our second equation, which I'm going to be showcasing it to you from a graph. Let's have a graph for velocity to time. Let's pick a starting velocity. Let's call this v0, and let's call this, or you know what, not v0, let's just say v initial, and this is v final. So if we have constant acceleration, let's say on the positive direction, for this example, it can also be in a negative direction, our slope is going to be the same everywhere. So if we're starting from this initial velocity, we're going to have the same slope for constant acceleration, and our graph, I drew that quite bad, our graph would look something about this. And previously, I mentioned the fact about integrals. I told you that the area under a curve gives us, in this case, a graph of displacement. So, to calculate this procedure, we can take these two parts as separate. Let's say that this area, the initial times, let's call this t0, gives us our starting point. And change in velocity, v final minus v initial, times t0 gives us our change in displacement. That makes sense, right? So if we were to take the integral of this geometrically, we would say that the final position is equal to the initial velocity times t0 plus 1/2 of v final plus v initial times t0. We just calculated the area of this triangle here. This equals to our initial position. And if we derive this, we can just say the change in our position or displacement is just equal to this area here. So 1/2 final velocity plus initial velocity plus whatever the change in time is. Our third equation is essentially the same thing with the second equation, but the only difference we're doing is that we are substituting the first equation for the final velocity into this second equation. What do I mean by that? We knew that the final velocity was equal to initial velocity plus acceleration times delta t. And we know that delta x is equal to half of v initial plus v final times delta t. We can substitute this right here, and we would get something like this. 1/2 times v initial plus acceleration times change in time times delta t. If we go further with it, we're going to have something like this: 2v initial times acceleration times delta t times delta t. And if we open up this parentheses, these twos will cancel each other out, and we will have v initial times delta t plus 1/2 the acceleration times delta t squared. This is our second. Now, our final equation is useful in some cases because you don't have to calculate the time in first hand. The equation doesn't value the quantity of time. And to get that, we need to do something like this. So we know that the acceleration is equal to change in velocity over change in time, right? And this means change in time is equal to change in velocity divided by acceleration. If we substitute this to here, let's look at what we'll get. Delta x is equal to half times the initial velocity plus the final velocity times delta v, which is equal to the final velocity minus the initial velocity divided by the acceleration. Now let's go further with this. This is equal to v final squared minus v initial squared, right? You see that? Divided by acceleration. Now we can say that v final squared minus v initial squared is equal to 2a times delta x. And this gives us our resulting equation. V final squared equals v initial squared times 2 times the acceleration times the displacement. This equation is handy in some situations because you don't have to account for time. And that is the end of our kinematic equations for constant acceleration. We will be solving problems about this topic in a further future video. But for now, see you later.